All right, CNT140, we're continuing Chapter 8. We just left off on power meters, so I'm kind of picking up right where we left off. To measure power, you'll need a power meter and a reference cable that we use as kind of the 0 point. Here's an example of a power meter. Here's two more examples of, this is actually a test set. This is the light source here that you can alter between 850 and 1300 nanometers for like multi-mode fiber. This over here is the actual meter end. This is the one that's actually taking the measurement, that has the sensor in that's taking the measurement of how much light signal has made it there. And then these would be either reference or test cables, depending on what you're hooking up. Right here, they remind us about making sure that when you're testing using these power meters, make sure you have the proper range. So if I'm measuring power, I need to make sure I'm set for dBm, decibels per milliwatt. That's the absolute measurement of how much light is getting through. This is it. Boom. If I'm measuring loss, I would need to make sure that I'm set for dB, decibels, and that would be a measurement of how much difference there is from the last measurement. You know, reference cable measurement, and then I hook up the test cable, how much loss was there between the two. Make sure I'm also using the correct wavelength. Our test meter and our test cable will be alternating between 850 and 1300 to test how those two different wavelengths of light function across that cable. To measure it, it's actually just a couple steps. You need to put a reference cable in, let the meter and everything stabilize, and then kind of zero it out. And then from that, I can hook up my cable that I'm actually going to test with to know how much signal has gone across, or if I want to do loss, how much signal loss there is. And here shows you kind of the hookups. I have a picture here in a little bit that shows this process a little bit better, so I'm going to keep moving. Optical loss is primary performance parameters of most fiber optic components. Yep. Fiber, there's a loss per length. Or attenuation coefficient. So the actual fiber itself has a little bit of loss. Each connector that you're using has a little bit of loss. And the total cable, the cable itself is the loss of all those components put together. The actual fiber, the connector, splices, anything like that, that would be loss of the whole system, if you will. To do loss, again, I'm using this meter setup, the meter and light source, and I'm actually going to, again, reference out the meter, zero out the meter, and then I add the test cable on, and that'll indicate or measure how much difference there was from the 0 point to what's there now, and it turns that into loss for you. So you actually have a loss measurement. Now, where that comes in handy is before I install a cable, I usually do a link loss budget. I kind of figure out how much loss should be there. And then when I install it and test it, it should be close to that parameter. If it's worse, then I know there's problems. Maybe some bad splices, bad connectors, that sort of thing. Then I would need to go in and do some testing and troubleshooting. So I would do a link loss budget first, and then I can compare that to what I'm actually measuring. Late in the lab, we will do one of these on our for our bid spec project. We'll do a link loss budget estimate for our bid spec process, just so you see how that process goes. And there's actually a calculator to help you do it. It makes it actually really easy to do. Okay, so testing loss, you'll need to first hook up a reference cable and basically zero it out. And then I will add on my test cable to this, and that will do the difference measurement. And again, here's the rough connections that you make for patch cable and installed cable plant. Okay, this right here is a little GIF I found that actually shows this process kind of very neatly, as for lack of a better word. So if I take a look here, it's going to loop around, and this is going to go back to the beginning. First thing, you hook up your reference cable and zero out the meter, so it's basically calls that 0. Put the connector in, add your actual test cable, and now it basically compares the original measurement to this one, and it gives you that number in loss. So zero it out, put your connector in, test cable in, and that'll give you the loss measurement. You should see down there, you know, negative 0.5 decibels, if you will, that kind of thing. That is how you test loss. That's actually how we're going to hook up our cable to test for loss. I believe this one shows you how to do for like a cable plant in a building. zero out again, connector, connector, and then this would be the cable plant here. So this kind of shows you all of it. All the connectors and everything then would be involved. So if I had to install, test an installed cable run. All right, the reference cable we're going to end up using is this guy right here. We're dealing with multi-mode fiber. We need to do some conditioning. If you remember earlier when we talked about fiber, you have the low and high order modes that are coming through. If I loop that around a bunch of, bends or circles, if you will, it tends to even it out to make it a nice, the long order light modes are the ones that end up making it through. The ones that are bouncing up and down kind of get filtered out, if you will. So we're going to use this right here as our reference cable, and in there the fiber goes around and actually does that kind of filtering out those modes that are bouncing around the fiber, not the ones that are going down straight through the middle of the fiber, if you will. Calculate loss budget. We're going to do this in the end of the lab. We'll actually use this calculator and calculate the loss budget on our bid spec project. And that leads us into what kind of loss should you get? Well, each connector, each splice will have a predictable amount of loss. And these are numbers that are here and also reflected in the calculator when you go to use it. So each splice has 0.2 to 0.1 to 0.2 for fusion splice, 0.3 for mechanical. Each connector has about 0.3 to 0.5 decibel loss. Single mode fiber has about 0.4 decibels per kilometer, and multi-mode fiber has about 3 decibels per kilometer. A lot more loss on multi-mode versus single mode. All of those numbers can then get used to basically calculate loss. And the total loss of the cable plant is all the connectors plus all the splices plus the loss of the fiber for its length, and that'll give you the total loss. And again, this calculator does all that for you, which is kind of nice. It makes that easier to figure out, to calculate it out. This was a chart that was in the book. It might not be in your edition right now, but it was in the book previously, kind of showing all those measurements that they just spelled out for you. So if it's a little handier to reference. The standard itself has loss factors to follow. Here, maximum insertion loss for multi-mode, single mode, etc., connectors, and so forth. So the standard has that spelled out as well. They remind us on some troubleshooting. They have a high loss cable. If you have a high loss cable, they say measure it. Basically, if you measure it one way, flip it around, measure it the other way to see if you get anything significantly different. If you're using a double-ended test, again, here's the reverse it as well. This is one down here, reverse it. Single-ended test the connector on one end, you can actually say a bad connector. Here, if it's a double-ended test, you can reverse it to see if there's anything that shows up. And then here, if you have no light coming through the fiber, they're reminding you well, it's probably one of the connectors, so you might not be able to isolate. You might be able to with the visual fault locator. You might be able to see which one's causing it. If not, they say, well, basically, kind of re-terminate one end, see if it does it, and if necessary, re-terminate the other end. OTDR testing, optical time domain reflectometer. We do not have one of these, but we will talk about and do some looking at the output of an OTDR to kind of get a feel for the kinds of things I would see. An OTDR is usually used on outside cable plants. So we're talking usually kilometers and many kilometers of cable length. It can locate faults, measure cable length, verify your splice loss is allowable, measure loss of a cable plant. That is kind of necessary for some of the other measures, so it can give you an estimate. But it doesn't measure optical power. That's where your power meter would need to come into play. Here's some examples of, I think this is the one that they showed you in the book, and they're showing you basically what the output looks like. It's a little graph output. This kind of thing is the graph output. It's actually showing you, I think this is 850 and this is 1300 nanometer wavelengths, showing you the result of that test. And we'll look at these little blips a little closer here in a bit. Again, mostly used on outside cable plant. It's widely used as your outside cable plant troubleshooting tool. Most OTDRs lack distance resolution for short cable runs. So we're not typically using these on premise networks. One of the reasons we don't have one, it's typically used on your outside plant. The power meter works directly. I have the source, and then I have the light source, and then I have the meter end, and it's actually measuring that signal strength coming through. OTDR works indirectly. It actually looks at the backscattered light. So as you move light through the fiber, some of it's going to get backscattered to you from connectors, splices, etc. So some of that light is getting backscattered to you. And from that, it can imply loss. So it kind of works on the premise of like a radar. You know, you send a pulse out and it comes back, and then you send another pulse out and come back, and it compares the two. And lets you know how far something has moved or the distance something is away from that. So you have your meter hooked up to cable. Here's the cable you're testing, receive cable. It sends a signal out and a pulse comes back. So we have the transmitter, receiver, and it uses those pulses to start graphing any events in the cable. So here shows you the idea of, you know, here's the initial launch of the signal into the fiber. This is your launch cable. So this lets you know the first connector, a slow attenuation over distance, the other end of the connector. So this lets you know, or a splice in this case, this lets you know to that event how much signal loss has occurred. Here kind of shows you that graph again, 850 or 1300 nanometer, 850 nanometers. And again, each of these little bumps on here means something. A large bump like that is usually a connector, maybe a patch panel or an actual connector of plugging in. And then a smaller little loss, that's where an actual splice would be. And then when I finally trail off at the very end, that's the end of the fiber. And that's all from, you send a signal down, it bounces back. Send a signal down, it bounces back. And it's letting you know where all of these are. Here's a little bit closer look at, you know, a splice along the way, connector, end. And I think I have another one here as well. Slow shows you the actual attenuation, how much signal loss you're getting. This is a reflections back from a connector and letting you know loss. A smaller drop like that is usually a splice, and then it trails off to the end. That's the actual end of the cable. There is limited distance resolution, so again, it's hard to use in a land building. It's mostly for outside plant fibers. In a short run, you're likely to have ghosts from the reflections. And I think I have some here showing you that I'm getting a ghost and it's like all kinds of noise over here. So you're not getting that good measurement from the distance. A little bit too short of a run. When using an OTDR, a few cautions. Make sure you're using that long launch cable. When you start sending pulses across, they say use the shortest pulse width first, and then increase as you need. And that'll allow you to start getting good results, because it's not just a once and done. You have to do a couple to get good results. Here's showing you here. Here's your launch cable, receive cable, and then the overall from here down to here is the overall end-to-end loss. And then you will often do tests at different wavelengths and compare. And again, this shows you the amount of attenuation at 850 versus 1300 nanometers. Here up here is the connectors. These are like splices in the middle, and this is the end of the cable run out here. So you'd run multiple wavelengths and compare to get a better feel for the overall picture of this cable. All right, I think that'll be a good place to stop. We will come back in the next podcast to finish it out.